it's a good amount of big picture and a good amount of technical. At the World Resources Institute, for the past year or so, we've been really shifting our attention to understanding how we can monitor trees outside of forested ecosystems. And this is some work that is utilizing CNN networks running in TensorFlow that I had shared with Karis and Timothy, and they thought it was appropriate for this working group. So I want to walk you through a bit of the stuff that we're doing with these remote sensing technologies, what we plan to do in the future, and yeah. So our team for this work is made up of myself, Fred Stoll, who's our Deputy Director of Forests, Katie Raytar, Bernadette Arakwi, and Jessica Ertel. I am the person who's doing all of the modeling and the remote sensing work for the project. You may know the World Resources Institute for our flagship platform, Global Forest Watch, which does annual and near real-time monitoring of forests at a global scale. But something that Global Forest Watch does really well is forests, and something that it doesn't do very well is all of the non-forested ecosystems in the world. So we have a pretty packed agenda to try to get through all of this work, as well as to have some time for discussion. I'm going to start with a short background on why this work is important, give you a little sneak peek of the data, walk through the methods in as much detail as I can. There will be a link to the code at the end. Talk a bit about how we've done accuracy assessments for this work, give you some comparison with the Hansen 2013 data, which is the data that's currently online and available on Global Forest Watch. Tell you a bit about the early successes and how we've begun to engage government partners with this work, and then briefly give you a sneak peek into our timeline for what we want to do going forward. As you may know, the World Resources Institute recently received $100 million from Bezos to do a lot of transformative work around climate, and this is one of the things that we hope to be doing going forward with that.
John, can I hop in real quick? I don't know
yes, please.
Can anyone else see the slides? Or am I the only one who can't?
Yeah, no, I can see it. I can't see it.
Cannot?
You can't see it either?
It says it's sharing my screen. Let me try that on here. Oh, here we go. You're right. I had to click one more thing. It says there's a. Okay, let me try that again. Thanks for that.
No worries. It was just, I didn't know if you're waiting for the slides to be to present a dramatic effect. Perfect. Yes, I can see them now.
Okay, perfect. I didn't know that
I'll give you the
Google Meet had that extra step. So here's the quick slide of our team that I'd already discussed. Here is, as you may know, the landing page for Global Forest Watch. Here's our agenda, the 7 things that we want to run through. And it's perfect because we were actually just about to get into the first slide that matters. So we really see a distinction between trees inside of forests, which are these dense closed canopy trees, both inside of contiguous and fragmented forests, as well as trees outside of forests, which are open canopy trees on agroforestry, trees on farms, trees in urban areas, trees on grasslands, those sorts of areas. And if we look at a global scale where these trees could be, one good way to do that is to take the ESA land cover data from 2015 and to clip out the forested areas and to clip out the hyper-arid areas. What you're left with is about 3 billion hectares of land. You can see zoomed in for Central South America and Africa on the right, where the data, similar, such as the Hansen 2013 data on Global Forest Watch, doesn't actually track anything about the trees in these areas. So what we have here is a monitoring gap of the potential carbon in these trees, as well as the tree cover and the land cover change in these ecosystems in these areas on nearly all of this 3 billion hectares of land at a global scale. Moving forward, there's a large international agenda around increasing the extent of trees outside of forests. This is known as forest and landscape restoration. One of the really sort of groundbreaking papers in this field was a Bastien paper in 2019 in Science that looked at what climatologically is the ability for different land covers and different eco regions around the world to support additional tree cover. The takeaway from this slide is that almost all of this map is green and yellow, which is between 0 and 50 or 60% additional canopy cover that most areas on the world can support. So when we think about doing tree planting efforts and things like that, we're not looking to make new forests. We're looking to plant scattered trees on farms and to do low density tree plantings in most of the world. But the problem is that our current monitoring systems can't actually track these open canopy tree ecosystems. And so in addition to the previous slide where we said that there's about a 3 billion hectare monitoring gap, or about the size of Africa in terms of trees outside of forests and their current extent, we have an additional monitoring gap of potential areas in the future where trees outside of forests may hopefully become established if the restoration agenda moves forward as planned, where we won't actually be able to monitor and report on this work and the additional effects that it has for carbon and for meeting sustainable development goals. So all of this to say that the global restoration agenda, such as the Bond Challenge, Trillion Trees, AFR 100, and Initiative 20 by 20, targets increasing trees outside of forests. And it targets increasing trees outside of forests, specifically on land covers that already have some trees outside of forests. So we have a problem when we try to set the baseline for these projects, and we also have a problem when we try to go forward and track change over time. So here's a quick visual to see what the monitoring gap looks like. On the top right is the data that's currently available on Global Forest Watch. What it is a global forest extent data layer. So it shows the forested closed canopy forests very well. What it doesn't show here, this is in Pará, Brazil, in northern Brazil, it does not show all of these scattered trees on pasture land and scattered trees on cropland. The data that we're creating on the bottom right is able to go through using the 10-meter freely available Sentinel data and target these individual trees, which are many times the size of or smaller than a single pixel. So a quick sneak peek of our data. On the left is the cover page and abstract for the publication, which I'll send out to the calendar invite after this call. And on the right is a quick high resolution image from Google Earth, as well as the predicted tree cover for that area in northern Guatemala. If we look at a bit bigger picture of a scale, this is in northern Guatemala, where we can see mosaic cropland, pasture land, and fragmented forests. We can see that this is a very mosaic, very dynamic ecosystem. And we're able to go through with free satellite imagery and accurately track the tree cover for this area. Moving halfway across the world into northern Ethiopia, we can see that we're also still able to, oh, this GIF is, there we go, to track individual trees on farms. So in order to do this, we're using a combination of the radar data, VVBH data from Sentinel-1, and the 10 and 20 meter bands from Sentinel-2. We're super resolving the 20 meter bands from Sentinel-2 up to 10 meters. And we're developing an annual product that is going to be global from 2017 to 2020 and then moving forwards. Our output is a per pixel % tree cover. And here is an overview of the methodology. I'm not going to talk about this slide. I just want to have this in the slide deck in case someone wants to refer to it. Instead, I want to walk you through basically the story of a tile of how we go from the satellite data all the way to the tree cover predictions for 4,000 hectare tile. This is all done on Docker containers on AWS Fargate. I know a lot of folks here on this call use Google Earth Engine. I'll talk a little bit later about why we have chosen to do Docker containers instead. But basically, we start with for input 4,000 hectare tile. We grab all of the 10 and 20 meter bands for the entire year. So something that I'll touch on in a little bit as we get to the TensorFlow model is we're actually doing time series networks. We're using convolutional GRUs. So rather than having a single mosaic image, we are looking at the entire year's imagery as an input so that we can then look at the senescence and the phenology of a pixel. So you can imagine if you have a crop and you have some trees on that cropland. if you take a single yearly composite, the NDVI and things like that might be pretty similar between the trees and the crop. But if you look over the entire year, if the trees have different leafing out patterns and different phenology than the crop, which is going to have a planting and a harvest cycle, you can see how this additional data can help a neural network distinguish between the pixels that are trees and that have trees in them and the pixels that are crops. Even if the pixels that have trees in them, the trees are covering a small fraction of the single pixel. So what we do is we get this whole year of imagery, and we use S2 Cloudless to create cloud masks, which you can see on the right, associated with the time step. We then implement a paper that came out in 2020 to do multi-temporal cloud shadow masking so that we can ID where all of the shadows are. And we basically aggregate the two, the clouds and the shadows, into a blob so that we know when and where to be masking and interpolating out the atmospheric effects from the clouds and the shadows. We use a paper called DSEN2, which is in the bottom left, to do a convolutional neural network upsampling of the 20-meter bands to 10 meters. This basically uses a CNN to minimize the loss between, they take the 20-meter bands, downsample them to 40-meter bands, and create a neural network that minimizes the loss between the learned upsampling of the 40-meter bands and the actual 20-meter bands. And then you apply that at testing time to 20-meter bands to upsample it to 10 meters. If you Google DSEN2, you can find the paper. It's like 5 to 10 times better than just doing bilinear upsampling. And then we take each of our, for each pixel, you can see in the bottom left, the reflectance here. This is band 0, the blue band, over each day of the year once we've removed the clouds. And then we basically generate a smoothed time series for each pixel on the right using the Whittaker smoother. And then we take that smooth time series and we generate monthly mosaics from that by just taking the median for each month. What this gives us is here on this left, as a mostly cloud-free and cloud shadow-free monthly mosaic. This is in, again, northern Guatemala, where it's cloudy 8 months out of the year. So there's a couple tiny clouds that are missed, but it does a pretty good job. And so we have these 10-meter super resolved bands for all of the 10 and 20-meter Sentinel-2 bands, as well as a couple remote sensing indices, MSAVI2 and NDVI, and the normal ones. We also take and calculate slope from the digital elevation model, so that the model knows what the slope is like, which helps it identify, because we're using temporal imagery, it helps it specifically identify terrain shadow, which is a big problem unless you have the slope. And then we also have our monthly mosaics of the Sentinel-1 imagery. Again, this is VVVH gamma backscatter decibel imagery. All of these three get concatenated and get put into the model. Our training data looks a bit like this. We have used Collect Earth Online, which is a platform that SIG developed to do our labeling. So we've gone in and basically, for about these 6,000 plots located on the right, identified every single pixel that has a tree attached to that 10-meter pixel, and then downloaded the Sentinel-2, Sentinel-1, and slope associated with those pixels. And this is what our model looks like on the top right. So I'm going to sort of walk through some of the code and the building blocks for this. But as you can see, if you're familiar with CNN models, this is a standard UNet architecture with some changes. The big thing to note from the get-go here is that we are doing the cropping in the UNet paper, where our input is larger than our output. So we're using a 24 by 24 input window to output a 14 by 14 prediction so that we don't have any boundary effects. So you can see the white areas that are the blue areas that are surrounded by white, those white areas get cropped before we do the concatenation. And I'll show you that code in a second. But the big thing that I want to talk about for this slide is the fact that we're using a convolutional GRU. which extracts spatiotemporal features from that input imagery, which is the monthly mosaics. You can read the paper for the paper that we wrote for this, as well as the paper for the convolutional GRU. But basically, it takes a GRU, which is a variant of a recurrent neural network, and it replaces the hidden and the internal states with a convolutional filter rather than a one-dimensional filter, so that you can learn time series representations of spatial features. The output of this is then a non-time series data. It's a single feature map, or a single set of 48 feature maps that then goes into the GRU. You can see the code here. Basically, we're using a conv GRU cell that has group normalization and some spatial squeeze and excitation. And then we're using zone out, which is a form of regularization for recurrent neural networks to do a regularization. Another thing I want to note on this slide is that we are using I guess I can actually talk about it on this slide. Rather than using ReLU and batch norm, which is really, really common, we're using swish and group norm. You can see that in the code here. We have our normal conv2D layer that's still, has the normal heat norm initialization and things like that. But our activation function is swish instead of a ReLU. This helps with dying neurons that you might see from ReLU. And then we're using group norm instead of batch normalization. We found in tests that this helps anywhere between 2 or 3% increase in accuracy. We're also using concurrent channel and spatial squeeze and excitation blocks, which you can also read about in the paper. These help improve per pixel accuracy. And then finally, we're using a drop block here as a regularization metric as opposed to drop out. This UNet, as you can, if you know a little bit about UNets, it enables you to combine high-level features with low-level features. So your encoder network is taking that 24 by 24 block and downsampling it to be 4 by 4. So as you take that 24 by 24 input and you squeeze it and squeeze it and squeeze it down until it becomes really small, what you're doing is you're increasing your receptive field. So each pixel on that 4 by 4 is responding to about a 16 by 16 window in that 24 by 24. So this means that that encoder, that 4 by 4 block, has this really, really wide field of view. So what we then do is we downsample it to become that 4 by 4, and then we upsample it to become the size of the output that we want, where we're also then concatenating the early features that have a really, really narrow field of view of only 3 or 5 pixels, so that we're then able to, at the output, the sigmoid is looking both at these really low-level features as well as these really high-level features at once, which is sort of one of the main tenets of a UNet, but I think it's good to reiterate its utility here. Here's what the code looks like. Again, I'll be sharing a link to this code at the end, but we have our GRU encoder. We have our different building blocks using conv swish group norm. And then on the decoder, you can see where there's the cropping 2D layer that takes the adjoining layer from the input, crops it to be the right size for the output, or for the decoder, right before the concatenation. So that's what the overall model looks like. One other thing that we're using that I think is really cool and really important to note is we're using the boundary loss in addition to cross entropy. What you can imagine is if you have labeled data that looks like this, some of it's somewhat ambiguous in terms of whether one pixel should be labeled positive in red or if it should be the pixel right next to it. And this is a problem when you have your per pixel cross entropy, because it actually says, this is the be all and the end all and the truth. If you are 1 pixel off, you are completely wrong. And if you're 1 pixel off, because cross entropy is exponential, your loss can be 14 or 15, as opposed to like 0.1 or something like that. So you can have really, really high loss values by being 1 pixel off. And given that these original labels are maybe not perfect, being 1 pixel off happens pretty quickly or pretty frequently. And so you end up having really unstable training. What the boundary loss does is it actually weights errors that are further away from positive pixels higher. You can see the archive link at the bottom if you're interested in this paper. It came out in 2020, I believe, so it's new. So you can imagine if we have a input labels here on the left where the trees are labeled in white, what the boundary loss does is it says, okay, this region over here, that's really far away from any of the positive samples. If you have a false positive or false, yeah, I guess a false positive here, then penalize that really, really strongly. But if you have a false positive that's closer to a pixel that's labeled as a tree, then don't penalize that as much because that might be an ambiguously labeled region. So we found that including this was absolutely instrumental to having the model train stably. Another thing that we use is called equibatch sampling. So basically, because we have this range of the percentage of the input region that is containing a tree that varies from 0% to 100%, and the input for this range of tree cover input is actually very, very variable. We found that if a couple of batches in a row selected either all zeros or all ones for this, that it could lead to the model diverging. So what we do is we implement something called equibatch sampling, where we ensure that for each batch, there's a sample that has between 0 and 10% tree cover, a sample that has between 10 and 20% tree cover, a sample that has between 20 and 30% tree cover, and so on, so that each mini batch is pretty similar to the other mini batches and the model doesn't diverge. Finally, as an optimizer, instead of using Atom, which is really, really common, we use Atabound. You can see the link to this in the bottom left. Basically, Atabound smoothly transitions from Atom to SPD as the model progresses. We found that this improved our test accuracy by quite a bit. You can see from the paper here that Atabound was initially reported in. Atabound on these CFAR10, so these computer vision data sets, outperforms all of the other different optimizers by quite a bit. So we selected this as our optimizer. It works great. Didn't have to tune learning rate or anything. We just used what was in the paper. Some of our other hyperparameters, we have zone out, drop block, label smoothing, the overall model size, just noting that we have equibatch sampling and whatnot. So that's the model itself. Here we're using drop block. So it's basically drop block instead of just doing random dropout like dropout does in B here. It instead drops contiguous regions and squares, which this paper found was a lot better than just doing normal dropout. So we use that instead. And this is all running on Docker containers on AWS Fargate. So basically, what this does is each Docker container takes in an input GeoJSON, which is the area that we want to process, and it outputs a path to a GeoTIFF on S3. We're using this rather than Google Earth Engine because we can really easily parallelize this across nodes. Because this is something, we're taking in monthly mosaic imagery, so we have 12 times the input data requirements from a composite. That we really, in order to get up to the speed that we need to process this at a contentful scale, we have to be running, we're currently running 10 nodes. We'll pretty soon be running 50 or 100 nodes, which will be 50 or 100 GPUs all processing this at the same time. And then we're using Terraform, which is a package that lets you manage Docker containers in order to algorithmically manage all of these different nodes. So finally, if we took our input back here, and I wanted to look at what the output looks like once we have run that through the model, it looks a bit like this, with the high-res imagery on the right and the tree cover predictions on the left. If we wanted to zoom in a little bit, you can see that we get these really, really high fidelity tree cover percentages and the ability to, in many cases, identify individual trees that are a pixel or subpixel size. We're doing also change detection on this. I don't think we have the time to get into the change detection methods, but that's the paper if you're interested in the change detection approach that we're using. We tested 5 or 10 different approaches and found that this one worked best. So yeah, we've done four different accuracy assessments on this. These are all in the paper, so I'm gonna sort of breeze through them a little bit. The first one was your standard accuracy assessment. You know, we have 1,000 plots distributed globally. That's the holdout, the test data set. We compare that to the baseline models, which are random forest, a support vector machine, and a unit. And then we break that down by users and producers accuracy across different regions, background, cloud cover, aridity zones, slope of the plot, and percent canopy cover of the plot. And you can see it on this chart that the proposed model performs best in every single situation. We also compare the data with the science paper Bastine 2017, which is the global extent of forests and dryland regions. In this paper, they hand labeled the percent tree cover of 500,000 plots distributed across the drylands. We took a 1% subsample of that and then calculated the percent tree cover of those plots with this neural network and found that the average disagreement was only 5%. You can see the heat map on the left there between the actual tree cover, which was the tree cover reported in this Bastine 2017 paper, and the predicted tree cover on the x-axis, which is the outputs of this model. And you can see that the R squared is above 0.9, and it matches up very, very well. So this was sort of our first external source of validation data. Finally, we wanted to look at the wall-to-wall maps in a couple different areas. So we looked in Ghana, in Tanzania, and in Honduras at these little 300 to 400 hectare regions, and labeled every single tree. You can see in column 2 where it says labels, I guess column B. We went into these 30,000 pixels in each of these and literally hand dotted every single tree. And you can see in the third column in C that the proposed approach that we're using is able to, in Ghana, identify these trees on farms, in Tanzania, identify these trees on farms, and in Honduras to really, really accurately distinguish the borders between the mosaic forests and the cropland. As opposed to the random forest, which has a lot of false positives, the UNet, which looks kind of blobby in a lot of cases and doesn't get these individual trees, and was currently available on Global Forest Watch, which again is a global forest extent data layer, so isn't concerned with these trees outside of forests at all. The last accuracy assessment stuff that I want to touch on before we get to the next steps for this work is comparison with this paper that came out in 2019, Zhang et al. This is Compton Tucker at NASA was involved in this paper. They wanted to use Sentinel-1 and Sentinel-2 to look at how, with a support vector machine, we could or could not map forests and trees in dryland biomes, because they sort of saw this similar problem that we've seen, which is that the global data sets right now don't really do well in these open canopy forests. They used this data that was labeled by Martin Brandt in a 2018 Nature paper, which is about 20 or 40,000 trees or something like that, solely located in Senegal, which you can see on the right here in green. These are all the hand labels. And then, you know, they took their training data set and their testing data set, and this is part of their testing data set. And they produced this map, which was part of their paper. You can see their predictions are in magenta. So you might look at this and say, that doesn't look very good. They can get these larger clumps of trees where there's 3 or 4 trees and pixels that are next to each other, but they don't get the individual trees. So what they report in their paper is, yes, okay, using Sentinel-1 and Sentinel-2, you cannot produce wall-to-wall maps. What they do is they aggregate this data to a 250 by 250 grid and say the aggregation bias helps them out, and they're able to track the percent tree cover at a 250 by 250 grid. But what's important to note is that they were using 20,000 labeled training points in Senegal. We're using the same satellites, so the same sensors and resolution, and they were not able to produce wall-to-wall maps. In our paper, we're also using Sentinel and Sentinel-2. We're using data that's focused at a global scale, so we actually had no training data at all in Senegal, and this is what our predictions look like on their test data set in magenta. So you can see we're able to dot 95% of the trees, where in the Zhang et al. Paper, they were only able to identify 30% of them. So what we conclude is that we're actually able to produce wall-to-wall maps of open canopy forests and drylands. The last thing before getting to the steps moving forward is to give you a quick comparison of what is currently on GFW there with what we're producing now. So you can see they line up very well in forested areas. This is in Makueni County in Kenya. But what the huge additionality is our ability now to track trees on farms, which are all these little dots that you see. We wanted to look at another spot. This is in Tanzania. You can see a very similar picture where the data matches up really well for the forested parts. But for all these trees on farms, we're now able to go through and accurately identify them. Some successes that we've had thus far, we're working with a number of jurisdictional governments to help set and track baseline progress around tree cover, specifically in Niger and Cameroon and Malawi and in Ethiopia. These are some of the 2019 tree cover maps that we've put together in collaboration with these jurisdictional governments. If you wanted to zoom in on some of them, this is from left to right. This is Kore in Niger, Mogazong in Cameroon, Araresa in Ethiopia, and Rumfi in Malawi. You can see our ability to, in these very dry regions of the world, to accurately identify tree cover and tree extent. And then finally, the last example that I want to give is doing actual change detection for tree planting projects. This is a project in Extrema, Brazil, which is north of Sao Paulo State, where the Nature Conservancy and some partner orgs are doing tree planting for basically these areas that are in white, these polygons, starting in about 2016. And what we can do is actually, again, as a test data site where we have no training data here, is to create a map that is in green the persistent tree cover, in purple the gain, and in a magenta the loss. So we can see within the polygons where they have actually gone ahead and done tree planting activities over the past couple of years. This is really exciting for us to be able to work with these sorts of projects to show their progress, to show, what we're actually doing isn't just, like it's actually happening. The trees are actually going in the ground and they're actually surviving. Here you can see some gain detection results from Guatemala, where we actually have half-hectare plantations, where in only 2 years we're able to pick up the change detection. So finally, I wanna get through goals and next steps so that we'll have about 20 minutes for discussion or questions. Basically, what we're doing is we're producing will be global, but this year will be Central, South America, and Africa, a static map at first of the extent of trees outside of forests, which will be all of the regions here that are not gray, with the goal of starting in 2022, doing change detection at a global scale as an annual product. Basically, we'll be mosaicing the data that's currently on Global Forest Watch, which is in green, with this new data on trees outside of forests here in blue. Probably won't be green and blue on the platform, but it'll look something like this, where you'll be able to see the trees that are inside forested ecosystems and the trees that are outside of forests. So that's what I have. This is the GitHub link. I'll send out I'll send out the paper to the calendar invite. Happy to answer any and all questions that you might have. Thanks for listening to this very, very fast version of this talk. Thanks. I'm going to leave my slides open in case anyone has a question about any slides.
Thanks so much, John. That was a fantastic presentation. I know that the slides that you shared with me before I think it was on the order of 60 or 70, 60 slides. So kudos for being able to move through all this material. I know that you said that you had just given a 2-hour version of this presentation as well. So, and I read through your paper. There's so much great content in here that I think is going to be useful to the TensorFlow working group. So I just want to say thank you so much for taking the time, for presenting your work. And I'm just going to open up the floor for any questions. So, anyone feel free to ask a question while we've got John donating his time for us. Thanks. Well, I will start the questioning. I will kick it off. So I was writing down a couple of notes, just thinking of things that I'm sort of running into as we're sort of trying to figure out an operational way to get some of these models working in the given regions for Severe, not necessarily focusing on a global approach, but these really regional specific models. And there's a couple really exciting things that I wrote down. Boundary loss, for instance. I thought that is something that we could potentially utilize and connect with a lot of the modeling that we're starting to kick off. Has these vestiges of Collect Earth Online because of all the work that Severe and SIG have done together, and seeing this figure that you have up right now helps to bring a little bit more hope to me that you're not going to be spending the rest of your life labeling data, and there's mechanisms here to have some weights connected to the platform already established. So that's really exciting, and I'll pause here if anyone else has got any more comments on just the novelty of incorporating this into some of the models that we already have. So that was my first real excitement point.
Yeah, Tim, just to sort of agree with you, the boundary loss is something that really interested me as well. John, could you talk a little bit about, what it was like to implement this loss function? Is it difficult, or is it sort of canned and you can just apply it?
Yeah, it's pretty straightforward. Hopefully you can still see my screen as I'm on my EC2 instance. Basically, it just takes this function that is calculating the distance map with sklearn, applies it across every sample in your batch, and then gives you a surface loss output there. There's if you read the paper, they have a link to both a PyTorch and a TensorFlow version implementation. It doesn't affect training testing time at all. It's super lightweight, and then we literally just use in our training like a alpha here that combines it, and then it just gets passed as a parameter to the model that combines it with cross entropy. So it took like 30 minutes to make sure it worked, and it improves stability a whole bunch. If you look at the paper itself, they show you how much they see improved stability, and I'd say that I completely agree with their stability improvements in terms of the oscillations of the loss. I'll show you one figure from this paper, which is not that one, I don't think. Yeah, maybe it was that one. Yeah, you can see basically with the boundary loss in the red one, basically over time it does better, and it oscillates less, and it doesn't overfit.
Yeah, that's really interesting. I mean, it seems such like maybe a simple concept, but I'd never even considered that. It makes a lot of sense.
Yeah, Yeah, literally it's just as opposed to cross entropy, which is this differential one, it's doing an integral one, which is the distance from the positive mask.
I see we have a couple hands raised. Phoebe, do you want to hop in?
Sure. Thank you, Tim. Thank you, John. This is actually a very good methodology. I'm happy with the results that are coming out. So mine is going to be more of comments and a few questions. And part of the things and challenges we've had, like in this region, is to more or less track those tree planting efforts. So I'm happy that this is able to do that. And the accuracy levels are also, they seem to be quite reliable. So it doesn't need so much training data. So part of the questions I have is there a certain age the trees need to get to for you to be able to detect them? That is one. Then the second one is with the definitions that countries have had over a period of time is there has to be like a certain group of trees that are contiguous in one location for them to be considered forestry. So with this new approach that technology is bringing up means that many countries now will start reporting more forestry than was previously reported. So what exactly does this mean for the policies that have been put in place for reforestation? Because for a lot of these countries, sometimes the trigger is, yes, we have diminishing forests, but now we'll be coming up with this message that we actually have more trees than we think we do. So that conflict management.
Really, really great questions. The first question on the age is something that we're working on right now. We are working through what's called the Priceless Planet Coalition, which is steered by MasterCard, where they are doing 100 million trees planted in the next 5 years in a number of different places in the world. We're basically tracking right now how long after planting we can see trees through this method. We're also working with a number of jurisdictional governments, especially in Brazil, where their legal code does specify there's like a legal impetus for tree planting. So that means at the parcel level, they know when and where trees were planted. So we found, for instance, in Sao Paulo State in Brazil, we can see trees a year or two after they're planted. We've also been working with some tree planting partners in Senegal and Cameroon, where it takes 4 or 5 years because of how slow the trees grow and the fact that they're doing direct seeding rather than sapling plantings. Our goal is to be able to know basically by ecoregion and by tree planting type how long after planting we can see this, hopefully within the next year, so that when we do release this data, that it becomes clear that this is the period at which it's seen by the satellite rather than the period at which it's implemented on the ground. With regards to your question on the legal definition of forestry and the numbers of hectares of forests, that is very true. Right now, we're starting conversations with a number of different countries on revising their NDCs, taking this new data into account before COP26. And that's something that we're trying to figure out is how this changes the baseline in terms of the percent tree cover for the country. A lot of the cases, though, actually this data is positive. There are a number of countries who haven't wanted to create NDCs around tree cover because they knew that the tree cover data was wrong for their country. There are especially a number of countries in the Sahel where the Forest Resources Assessment from FAO or the Hansen data says that they have really, really low tree cover, and their internal forestry data says they have quite a bit more. So we're hoping that this aligns the country data with the global data a lot better and helps those countries feel more comfortable doing commitments at a global scale. And then the other thing I would note on this is that around your comment about having more tree cover than more forests than previously reported, that is true, though this will not change the extent of intact forests. This would all be either trees outside of forests or mosaic or mosaic forests. And what we do report on and what the World Bank does report on each year is the the tree cover loss of intact forests, and we don't think that this number will change the extent of intact forests. So hopefully the messaging around deforestation and its impact will stay clear year over year. I hope that answers your questions.
Yes, thank you very much.
Yeah, great questioning, and I think there's so much more here to discuss on this topic, especially. But yeah, I'm glad that Phoebe, you brought up the real world implications of map production and what that really means, and so I'm so happy to hear that that discussion point was brought up as well. I see a couple more hands. Syed, do you have any questions?
Yes, thank you for giving your time. I'm Burhan Atal, working with ICMOD under Surveyor HKH program, and I'm responsible for land use land cover monitoring system for Afghanistan. It was very interesting presentation, and the problem we are facing in Afghanistan, I think we can solve that problem through this work. Actually, in Afghanistan, as we did the land cover mapping from 2000 to 2018, and according to our ground information, there is a deforestation. But when we saw in the mapping, we did this land use land cover on Landsat with 30-meter resolution. So, according to our ground information, the deforestation occurred, but when we are checking and map, there's not too much deforestation. Actually, in Afghanistan, the deforestation occurred that number of trees are decreased due to the deforestation, but area is not decreased. That's why we didn't detect any deforestation area in that. So I think this can solve that our problem. We can know about the actual area of forest area. It will be better to share this presentation with us, and also if it's possible, the coding, we will try to apply this for Afghanistan also. Thank you.
Cool. Thank you. I put my email here in case you wanted to email me. We've been primarily focused on Latin and Central America, or sorry, Central and South America as well as Africa for this work. But we have been working with FAO Pakistan around some of their restoration projects in northern Pakistan to develop tree cover maps and have found good results. So I wanted to put that out there. Also, we are working on a as of yet unreleased new data product called the Dynamic World Map, which is a 10-meter land use land cover data set for the whole world. Which, if you are interested in comparing the results there in Afghanistan, we can get you added as an early user to that to see if it lines up with your data. Otherwise, yeah, the code for this will be available, and if you're able to use any of the pieces for the model to help your model, I think that would be great.
Thank you. And also, we have already collected data for the forest. We have different kind of forests, for example, pistachio and shrubs. We have open forest, closed forest. So we have already collected data for national level using the Collect Earth Online. We can share that also with you. And thank you.
Yeah, definitely. Yeah, please reach out. I'd love to chat further about that.
Sure, I will. Thank you.
Thanks.
Well, fantastic. Yeah, great touch points there. And Syed, I'll throw myself in that conversation as well, because I think that's so important, not only for Afghanistan, but for just the HKH region on a whole as well. So yeah, I think you're underselling how much data you guys actually have and the work that you put in thus far. So I think it'd be a nice connection point here. Perfect. So I know we have only 6 minutes left, so I see one more hand up, and I'll give it over to Ate. And other folks, feel free to put up your hands too. But Ate, do you have any questions?
I have many questions.
Okay.
Thank you for the presentation, John. I work with Spatial Informatics Group in Severe Mekong Hub, and we are trying to achieve many of the things that you're presenting, but don't have the advanced level yet. So we're going to study your code in your papers very, very carefully. But I was wondering, for the model that you're using, what is the number of input layers that go into the model?
The input layers, meaning the bands and indices and whatnot, or the depth of
Yeah.
the model?
Yeah.
The input is the 10 and 20 meter band, so that's 10. The slope, which is another one, so that's 11. For remote sensing indices, we have the Enhanced Vegetation Index, MSAVI2, Bare Soil Index, and NDVI, which is another 4, so that's 15, as well as the VV and the VH Sentinel-1, so a total of 17. So the input's the 12 monthly mosaics of these 17 indices split between Sentinel-1 and Sentinel-2.
Okay, and all the mosaics, they go into the model at once, or these are different models?
They go into the model at once because this is a recurrent neural network. That's this first one. So this whole these monthly mosaics all go in, similar to how a recurrent neural network is modeling like a whole sentence at a time. If you're doing natural language processing, this is a recurrent neural network that is modeling the whole time series at a time, which is how we're able to get these sort of senescence and phenology data.
Got it. But with how many variables do you end up with in the whole complete model then?
280,000. So it's actually pretty lightweight. Here, where is the data on that? Yeah, sorry, 280,000.
Okay, that's pretty small then, from that perspective. Yeah. And how many patches do you use for training in total?
Only these 6,000 here. So we actually have very little in the Mekong.
Okay, and how do you handle the scaling of those different variables, especially for the indices?
They are min-max scaled, but with the first and the 99th percentile to remove outliers. So if we basically look at the code, where is it? So we're basically going through, clipping it to the first and the 99th percentile, and then doing a min-max scale.
Okay, and for the Sentinel-1 inputs, what additional pre-processing steps do you use there?
It's the GRD, so the ground range detected multi-looped data that has had noise reduction applied and is orthorectified to the 30 meter DEM.
And what software have you used for pre-processing the data?
We actually just get it straight from Sentinel Hub. We have a license with them through ESA. So they release the Sentinel-1 data as a GRD file that's already been multi-looked, already been calibrated, thermal noise reduction, radiometrically corrected, and orthorectified. So we were able to pull it straight just from a bounding box and get the data all pre-processed.
Okay, that's probably processed by Snap then, I would guess.
I think so, yeah.
Okay, that is great. Okay, we're gonna study your work in a lot of detail.
All right, please reach out if you find any bugs or if you want to know more.
I'm gonna bug you with many questions.
Great.
Okay, well, Ate, I know we only have 2 minutes left, and I think there's more questions to come. I'm just going to pause here and just say thank you so much, John. Honestly, this is a really great presentation. You can tell that there's a lot of excitement in the working group, and I have far more questions that I didn't get to ask either. And to that, with 2 minutes left, I'm not going to put you on the spot, but I think it would be really fantastic to have you come back and present some other work that you're working on, maybe not published stuff or anything that's sort of exciting as well. So we can definitely have a dialogue if you want to have another slot to present. And I'm sure there's going to be plenty of conversations from the various hubs on how we can interact. So thank you again.
Yeah, for sure. There's tons of work that we've done around how we've done all the hyperparameter tuning for this work, how we've set up a lot of the design that I'd be happy to share, because it's, I think, some of the things that takes the most time to figure out, which is not the stuff that I presented here today.
Fantastic.
Cool. Well, Well, thanks so much, everyone, and please reach out to this email if you have any questions. Happy to answer as best as I can.
Perfect. Yes, thanks so much. And I will put the recording on the TensorFlow website with the slides and the paper as well. So John, you don't have to do as much work.
Thanks so much.
Yeah, thanks everybody. See you in 2 weeks, and thanks again, John.
Yep.
Thanks. This was great.
Thank you.
Have a nice day. Bye.
Thank you. Bye bye.
Thank you. Bye bye.